All right, so this brings me to this point of the book that is called thermal resistance, which is an awesome, awesome concept. And it comes from here. The EE people know that voltage is proportional to current. This is for the EE people. I believe none of us is that, and it's a good thing. And this proportionality constant is, what is that proportionality constant called? Resistance, right? Resistance. And because they beat us to a punch, they gave it a name and they call it in ohms and everything. But we're going to steal the name. We're going to call it resistance 2. It's not going to be measured in ohms. It's going to be measured in something else. But you realize that if we say delta T is proportional to Q. This is what we said here, right? And it's more, and I didn't put the bars here because we know things flow from hot to cold. So what we're going to say is this delta T equals thermal resistance times the heat flux, the heat flow. Now, we can define this will be now thermal resistance. In the book and in class, we're going to be using the same sign R. And the reason is we're not going to be doing anything electrical here, so we're fine. But if you have electricity and heat transfer at the same time, you should use two different signs, two different symbols. Okay, so you know how I'm going to define R? As delta T over Q. Right, and this is R is positive because in reality I'm talking about absolute values. Right, I'm not worrying here about the minus sign and all that stuff. So what? Okay. With this concept, you can solve very complex problems very easily. The question is if this definition is good only for conduction. And the answer is no. And that's the power of it. I started with conduction. And I'm going to tell you take you amazing places. But you realize that delta T and Q happen in conduction, happen in contact, happens in radiation. Right? Let's go one step at a time. I'm sticking to conduction right now. But that's the beauty of this concept. So what is the advantage? We can make analogous or analog, I don't know what the proper, let's call it analog, that is a shorter word. Analog circuit. So now we can say that between this temperature T1 and this other temperature T2, we have two resistances in series. We're going to spend the whole next week seeing what cases like this. You know what this is? This is a heat exchanger. Actually, in a heat exchanger, you have many more resistors than this. You have fouling, you have convection, you have conduction, you have fouling again, you have convection on the other side, right? And if you were to do it by brute force, you die. But if you do it like this, very quickly, you have an answer that is of practical value, right? Today, I'm giving you all these theoretical concepts. But if you go to the notes we have uploaded, you're going to see how many examples are there. And so this is essential for heat exchangers. There is another one. This is called a series, and this is called parallel. Which is which? Tell me, if the wire represents the heat flow, right, and this represents the thermal resistance, do these two resistors see the same heat flow? They do. It goes from here and there, right? It doesn't get lost. For example, this would be a double pane window. The same heat goes through a succession of resistances. In this case, do you think they see the same heat? No, they know. Some heat goes here, some other heat goes here. This is a parallel circuit. For example, if you have convection and radiation, both are operating at the same time. So some heat goes by convection, some heat goes by radiation, right? Right now, these are just words, but we're going to get deeper into that. Another concept I want to bring in is this concept of R double prime, which is delta T over Q double prime. Now, this notation is horrible. I cannot find anything better because R double prime is not resistance per square meter. If you do this, you realize that this is Q over A is, so we would have Q delta T over Q times A, which is R prime times A of reference, right? And this reference area in a window is a trivial thing. In a cylinder, like a heat exchanger, it's not trivial because the inner surface is smaller than the outer surface. Sorry, thank you. So, thermal resistance. For a wall, we said R is delta T over Q. And we said that Q, right? And we said Q was K times delta T over L. We had said that just today. So we end up having that the thermal resistance of a wall is, oh, and I forgot to put the A here, right? Is L over Ka. And the resistance per unit area is going to be L over K. So the practical thing of this is that if you know the thickness of your wall and you know the thermal conductivity, you can already calculate the resistance. And guess what? When you buy insulating materials, they come with this R value. That's it. Right? So that's pretty cool. Let's stop here and pick up on Monday. Have a good weekend.